Hello everyone, thank you all for coming this evening. My name is Jack, I'm the Editor-in-Chief of the LSE UPR blog and journal, and I'll just quickly explain how this fits into our mission with the blog and journal, and then I'll hand over to Manav, who will introduce the team and sort of what we're going to be doing with this course as well. The UPR has just been set up in Michaelmas term last year, and our aim really is to get undergraduate students to take more of an appreciation of the research and ideas that they're engaged with here at LSE during their time here. The LSE UPR course is sort of trying to facilitate this process for students who don't really have a background in statistical research methods or just want to understand them more, because we think that you need it for a greater appreciation of the social sciences and sort of the joys of social science research. You should have an appreciation and have a chance to understand some of these really interesting research methods that Manav and the team are going to be introducing you to. So I'll hand the floor.
Okay. Well, just quickly.
I've also circulated the biscuits as well, so if you want to stock up while Manav's going to be talking, please do grab some.
So I thought today, as this is the first lecture, kind of go through some of the about why we started this course, introduce you to the team, and kind of talk about the course structure over the next 10 weeks. Yeah, so I think I'll get started. So in terms of the core content that we'll cover in this lecture, by the end, I think you'll start to understand how we can use very small groups to answer very big questions. And this is actually kind of the center of like what statistics does most of the time, because we don't have access to big groups. We'll cover that. And then a few concepts that might seem alien to you at the moment if you've not done a statistics course before, such as statistics, parameters, and variables. And by the end, I think hopefully you'll be quite comfortable with those concepts as well. But before that, some housekeeping. So we've been designing this course, but I think we designed it last term essentially. It's been 10 weeks, and it's been a real team effort, so I thought I'd kind of introduce you to everyone. So we've got Anna, who will be teaching so I'll be teaching the first 3 weeks, and then Anna will be teaching the following 2. And then Luke, who'll be talking about regression. But we also have Benjamin in the back, who's you've probably seen a lot of emails by him, and who's been informing you about the course. So yeah, and I think he'll probably continue to keep you updated on what's going on there. In terms of the time of the lectures, it's going to be every Thursday from 5 to 6, and it's going to be in this room here. But for the final 2 weeks, as LSE room booking is not great, we'll need to confirm what happens there, but hopefully we can get this room for those 2 weeks as well. And the other thing is we're going to head to the pub, so feel free to stay back if you aren't too busy. And one of the ideas of this course, beyond providing kind of teaching an introduction to some of the statistical concepts used in quantitative research, was also to create a community where people can talk about research and discuss ideas that they find interesting, because LSE doesn't often provide undergraduates kind of a structured way to do that. And so yes, if you can talk to people if you've come up with interesting ideas and you want to write about something, you have the LSE UPR blog to post it on and the journal as well. So I will, so before I talk about what is econometrics, just in terms of the course is really focusing on the intuition behind these concepts and avoiding the often mechanics that goes behind the mathematics. And hopefully I think by the end you'll realize that often the maths isn't that necessary, it's there just to provide a formal structure. And it's really about those bigger ideas that we want to focus in on this course. And the focus will be on interpretation, so hopefully when you're reading through papers you can look at the methodology section and understand what's going on. Or look at the back of like a paper where you've got the regression tables and understand what the numbers are really saying. So through this course I'll be often using the word econometrics, and so I just wanted to clarify before I start what I mean by econometrics. So econometrics is a subfield of statistics, and in particular it focuses on providing quantitative tools to study the social world. The reason it's separate from statistics is because statistics departments aren't often interested in the social world and hence don't necessarily develop the tools for that, whereas econometrics tries to do that. Now, econometrics has various applications. One of them is kind of descriptive study. So if you've seen Capital by Piketty, that's an example of a very detailed descriptive study of like 200 years of data. And then another common one is causal inference, and this is what the course will focus on. So by causal inference, I mean, are you here for the course? Thank you. So by causal inference, these are questions about does A cause B, and it's about the causes of things. So this would be things such as does an abundance of natural resources lead to instability in governments, or could be very micro, such as do smaller class sizes improve the students' performance in terms of grades and lifelong income. And this is where really econometrics is kind of different from statistics, because statistics often focuses on tools to highlight correlations, and in econometrics what we really want to separate is when do we have correlation and when do we really have causation. And so that will be predominantly the focus through this course. It's also used for forecasting. We won't really be touching on this, but this is mostly in financial world. This is used to forecast things such as risk in the future and volatility, or like what will GDP be in 2 years. But yeah, we won't really be touching upon that aspect. And I'll be focusing on causal inference. I think this is how the course fits in terms of structure. I think the slides kind of messed up and gone there, but anyway, this is how the course will be structured. And I think this would be something you're probably quite familiar with. So in any research project, you probably start with the question, and then you identify exactly what type of data you need to collect to answer that question. And then from the data, you need to answer that question, which has implications, and leads to further questions in social sciences. As you'll see throughout the course, what we'll be teaching kind of fits into in one of the 3 areas. So today we'll mostly be focusing on experiment design and data collection. Okay, so very quickly in terms of course structure, the first 3 weeks are on statistical inference. This is kind of the framework that underlies all the tools we use in statistics and econometrics. So here I'll kind of give you the big picture idea of how, like, what we're doing when we're collecting data, when we're collecting data, is it meaningful, when is it not meaningful. And so that's going to be the first 3 weeks, so it's going to be on the framework. Then once we've got that framework, we can kind of move on to actual studies and actual experiments. So we've got the next 2 weeks will be on randomized control trials. That'll be taught by Anna. So we'll cover theory on RCT. So RCT is kind of a technique borrowed from medicine, and now RCT is often used to see if for example, does a new cancer-saving drug actually work or not? And now it's being used in social sciences to find out whether A actually causes B. And then in week 5, we'll cover an application of do employers racially discriminate, which was a very interesting study done in 2003, I think. Then the final 3 weeks will focus on regression, because more often than not, it's not feasible to do experiments because a lot of questions, like if you're interested in the negative impacts of war, it'd be quite unethical to carry out an experiment for that. But unfortunately, experiments, it has occurred in the past, and you can use that to find out about what happened there. So that's what the kind of final 3 weeks will be focused on, and that's going to be taught by Luke. And the very last week, I've written quasi-experimental design here, but I feel I'll kind of gauge the mood of what people want to cover in that final week and kind of suit it towards that, but I think this will be an interesting topic, but this is subject to change. Yeah, and so some final housekeeping stuff. So we'll be uploading the slides on Facebook. It says before the lectures, which I did not do this week, but it should happen for next week. I'll upload it after, and then this lecture is being recorded as well. So if for any reason you can't turn up in a particular week, that should be uploaded afterwards. And yeah, as mentioned earlier, that room is wrong, and this one is 2.12, but we should be here at least till 3. And then 10 or 11, we'll beg Alice to give us some. Okay. Does anyone have any questions at this time? Okay. So I think I'll start with the actual content. Feel free to stop me at any stage if you don't understand something. And I'll try to give some pauses to the lecture if you have to. So we'll be covering descriptive statistics and population versus sample, and this will make sense in a bit what I'm going on about. So I think it's best to start with the historical example. So for a second, imagine you're James Lind. So he was a surgeon in the Royal Navy, and he was on a 2-month expedition. And a lot of sailors on the ship were afflicted with scurvy. Now, scurvy is a big problem in the 1700s, and as naval expansion was happening, a lot of sailors died because of that every year. So I think during his time, just 7 years before that, 1,400 sailors had died out of a 1,900 in the Anson's circumnavigation. So now, Lind had a hypothesis, and his hypothesis was that scurvy is caused by the lack of acid in the body, and that giving people citric fruits will cure that. Now, so imagine you're now on the ship and the people afflicted with scurvy. So how would you go about trying to test this hypothesis yourself?
You divide the soldiers into 2 groups. You feed one regular with citric fruit and the other you don't. When you observe, it's going to make any difference.
Yeah, so, but what about the composition of the groups? Does the type of people you put in the 2 groups matter?
And so the risk of the training beings.
Yeah, so that's actually precisely what he did. So he actually ended up testing a few more hypotheses than that. So he took 12 sailors. So I think today this would not be acceptable as a science experiment, but back then this was okay. He took 12 sailors, and he put them in, divided them in pairs, and then to each group, so that gave him 6 groups, and then gave them different treatments. So for us, it's group 5 that's what we're interested in. And what was found that, so it wasn't a great experiment because they actually ran out of fruits. But it was quite conclusive. What they found was one of the sailors had recovered completely, and the other one was just about recovered too. I don't know what happened though after they stopped eating fruits, but so that was the situation. And I think what I want to highlight with this example is that we kind of already have an intuitive idea of what we need to answer hypotheses and come up with causality. And what in statistics we're really trying to do is formalize and put these ideas into a systematic framework that we can implement repeatedly and consistently. So here I've just kind of written down some key aspects of the experimentation process. So firstly, there was a clearly stated hypothesis, and the hypothesis was that people get scurvy because they don't eat enough acid. That for reasons vitamin C, which is also an acid. But and then the second thing was he identified a group of interest. So that's individuals with scurvy. And then you also need to identify a treatment to test that. So the treatment was giving people citric fruits. And then there's an outcome of interest that we clearly know that we want to observe, and that's the health. And so he kept I think a daily record of what people, those groups' health outcome were. And then finally, you want to identify things that might affect the outcome, but aren't your treatment. So when you're picking your sailors, you want relatively similar sailors in each group. So it is a valid comparison, like an apples to apples comparison. So for example, if you had a group, 2 sailors who are 60 years old, another group of 20, it might not be a meaningful comparison because the outcome might be due to their age. So you need to clearly identify other things that might affect it and kind of try to keep them constant. And then finally, to actually conduct the experiment, more often than not, you can't actually find every individual with scurvy, because this is really a question, I think, bigger than this, which is about humanity as a whole. It's asking, do humans, when they don't have enough acid in their body, get scurvy? But we can't conduct an experiment on all human beings, so you take a subset of that. And so in the example, he took 12 sailors on the ship. So the question in statistics, the key question you're really trying to answer is, once we have this small group of people, these 12 sailors, can we make a meaningful conclusion about the entire population that we really care about? Because the question is about all humans with scurvy or all humans in general. And and then once we've done an experiment, are we saying something meaningful about humanity as a whole or not? So that's really what statistical inference tries to get into, and that's what we'll be exploring over the next 3 weeks. So to explore it in a systematic manner, I need to kind of introduce a few key concepts that we use. So the first concept is the difference between population and sample. So earlier I was saying that there's a clearly stated hypothesis which identifies which group you're interested in. So if you have another question which is about does health insurance lead to better health outcomes for individuals? Does having nationalized health insurance? It might be, for example, in the UK, does NHS? So then that'd be all UK citizens is the group you're interested in. But often it might not be possible to do an experiment on UK citizens, so we might collect a sample of 10,000 random UK households. So I've got a few other examples here, the scurvy example we just discussed. And if you're interested in salmon in the Atlantic, you might do 1 in 1,000 caught salmon, so where you're in different regions. So the sample is the group that we actually conduct the experiment on, and the population is the group of interest. Next week we'll go more into detail about how exactly we collect the sample, and that's quite important, how we collect it, in terms of what conclusions we can draw about the population based on the sample. Does anyone have any questions? Okay, so now once we've identified the question or the hypothesis we're interested in, the next stage is to kind of list out what we're going to measure. So in the scurvy example, we were interested in the health outcome, so we want to measure the health. And then we also want to measure the treatment we're giving them, so whether we get what treatment we give them, that's something we want to keep a record of. But also other characteristics that we believe might affect the individual, so things such as their age, their weight, their height, and things such as that. So here I've put a bit more of a formal definition of variables. So it's any characteristic, number, or quantity that can be measured or counted. And they have two properties. One is that it describes some person, place, thing, or idea. And the second is that the values vary from one entity to the other. The second point isn't that important, but essentially tries to highlight this idea that let's say if you've got a group of 10 people and one variable is identical for everyone, it's not a very meaningful thing to measure because it's not helping you identify, separate the people. Now, this is something that comes up in papers, and they often use fancy math notation to represent variables, so I just want to quickly kind of go over that. So I think the best way to think of a variable is through Excel sheets. I know Excel sheets sound very exciting, but I have to disagree with you. Okay, so the variable is kind of your table title. So if you've got a group of 12 sailors, then you might have their names as one of them. You might be interested in whether you give them the treatment. You might want to measure the age. Yeah, so let's say of those three. So this would be your variable. And then your observation would be something that's on each row. So imagine I was in the research, so that's my math. And let's say I wasn't given the treatment, so I put a 0 maybe for not getting the treatment. And my age is 20. So I'm going to use you as an example, Jack. Let's say you were given the treatment, you're 20 years old. So you might have a table like this, and you might, in big studies, you might have like over millions and millions of observations if it's a national census data, for example. So in papers, often the way the notation works is that, so you'd have something like name and an I subscript here. And often this would be abbreviated further, so they might just have NI or XI and so on. So the big thing here kind of identifies the variable, and the I identifies the observation. So I'll give an other example of age. So if you have age, and then the observation would be for me, so that'd be minor, and so that would be equal to 20. So in papers, when you see notation in that structure, so the big one is the variable, and the small one the letter. So more often than not, it would be something, age might be abbreviated to X, and then you will have I there. And that would just mean that you are talking about the variable, because I just means for some individual. And X will be the variable you're talking about. And variables can be in many forms. So you can have like numerical variables such as age and height. You can have discrete variables such as sex and race, and that's something that's quite important to highlight, that often in research you're forced to categorize things, but it is always a critical act. For example, to categorize sex as 1 and 0, and similarly race maybe as several numbers representing each category. They can also be just words, but more often than not, because we run these programs on computer software, we're forced to convert them into numbers. And also, in terms of names, in most studies, it's good to keep your sample anonymous, so we'll replace names with numbers as well, and your computer just deals with that better. Yeah. Does anyone have any questions?
So people are very complicated, and they probably have lots and lots of variables associated with them. Is it more of a good? Is this more when you're looking at variables and say trying to control for them? If you're doing a sample, is that more of like a good faith exercise where you're just trying to do your best, or is it more of a sort of scientific procedure of trying to measure the variables that you can and then controlling for them?
So do you mean when you're conducting the study and which controls you pick for the study?
Yeah.
So when you practically go do a study, more often than not, so there are 2 types of studies you can do. So if you're in the position where you've got a lot of grant money for some reason and you are going to do the experiment, then you can, then you kind of sit down and you might read past works and kind of understand what things might affect it. And you want to capture the meaningful effects. So, for example, if your question is about economic growth, probably hair color of people doesn't impact it so much, and you probably won't bother measuring that. So in a sense, you always need to go into theory with research, and in that sense, it's always a creative process when you're doing research, because there's no clear scientific way to identify them. But there are techniques, and this will be discussed in week 4 and 5 with randomized control trials, where actually you don't need controls, and it's because of the process by which you can collect your sample. So often data that we use, such as census data and so on, hasn't been randomly collected. So a lot of the background characteristics might match. I'll give an example. If you're curious on the question of do people believe in, what proportion of people believe in God, and you just collect data from, let's say, church-going people, then you have to kind of control for church-going nature. But if you just randomly pick people in society, it's not that important to control it, because there's no systematic background characteristic that kind of creates the data. So, does that answer?
Yeah, that's helpful. Thanks.
So now, when we kind of take variables into an experimental framework, so you might have done this in science GCSE if you did GCSEs or whatever school background you're from. So we can split it into 3 concepts. It's not too important if you don't remember them, but I think it's a good idea just to go over them once to. It's a good, I think, framework to use when you go about doing your own research. So your dependent variable is the outcome that you're interested in. So in the scurvy example, that's the health of the sailors. And it's called dependent variable because it depends on all the other characteristics that you're measuring about. Now the independent variable is the thing that you want to change. You might realize that this is actually language from the natural sciences, because they actually have control on changing these variables. In the social sciences, you're often just given them. But yeah, so the independent variable in the scurvy example would be giving people citric fruit or not. And then the control is everything you want to ensure that might be affecting the dependent, but you want to keep them constant. And here again, as I was just mentioning earlier, like you need to kind of make a judgment on whether you think it's going to be an important variable or not. And you need to defend that you have captured all the key important variables. Otherwise, people will throw the paper away. Yeah. Okay. So let's say once you've kind of collected that data, and now you have that massive Excel sheet with all these random numbers. That data in itself is not meaningful, and it's not really information. It's just like a data dump there. So often you need to convert those into meaningful concepts. And so you might remember 4 of these from maths in school, and those are mean, mode, median, and range. We won't really be covering most of them. We will only really need 2 of them, and in most research we only use 2, which is mean and variance, which I'll talk about in a bit. So yeah, so these measures help us describe the data and answer our hypothesis, because more often than not, our hypothesis is about kind of one of these measures, rather than the concept itself. So for example, in the scurvy example, we want to know what's the average impact on individuals of taking lemon and taking citric fruit. And the reason we often do it for these concepts is not just taking what is the impact on the individual of eating a lemon. The reason for that is that we can't necessarily know why it worked for that particular individual. Because there might be some background characteristic about them, and the body might function in a particular way that it worked for that particular individual. So often when we state hypotheses, we often state them about bigger populations and large groups, because on average things tend to work in a particular way. Yeah, so when constructing measures, we need to be very careful about what exactly are we measuring, because often we have a sample that we're making measurements about, but we want to make conclusions about populations, and so that's what we're going to kind of try and next I'll try to distinguish between those 2 ideas: measuring things about samples and measuring things about populations, and trying to reach conclusions about them from the sample. Okay, so actually before I go on to this, does anyone have any questions for these 2 new concepts? Yeah, so we've got 2 concepts. One is a parameter and another is a statistic. Statistics gets its name from the second type, which is a statistic. So I think first I'll start with parameters. So parameters are measurements about the population. And this is what we're really interested in. So we want to know the average impact of eating citric fruit, for example, on the entire human population in terms of scurvy. But often we can only measure things about the sample, so our 12 status. And those measurements are called statistics. So statistics is anything that describes the sample you have on hand. Now, when you're distinguishing between population and sample, it is quite an arbitrary line you draw. It is something that you do as a researcher yourself, so it depends on the question you have. For example, if I had a question about the people in this room, this would be my population, and probably I would be able to collect data on everyone, so this would be my sample too. But most questions aren't, I'm sure you guys are great people, but it's not that interesting question to do with people just in this room, and it's more about bigger populations. So more often than not, we need to kind of be clear about this. Yeah, so our hypothesis make claims about this, but usually we can't observe them, and that's basically the crux of what we're doing in statistical analysis, going from one to the other. Right, okay. So I'm going to quickly move on to now measuring data, and measuring data in the population and measuring data in the sample when we talk about statistics. So I remember when I put this in a computer program, I had a story behind this I would tell you. Now I seem to have forgotten it slightly, but I think it was on school children's heights. So one of these, one of these, okay, so these are 2, this is the population distribution. So on the x-axis I've got the height of students. And on the y-axis I've got the frequency. So kind of if a lot of people bunch together here, it's at 180. 180, that means a lot of people have a height of 180. And I've got 2 different populations here. So kind of ignore this graph for the moment. And when I made these the hypothetical situation I came up with was that one population is a population of men at university, and the other is of boys at school. So the question I want to ask you is, which one do you think relates to which group, and why? So in university, I would probably expect the people to be a lot taller, just because of the age difference. Oh, sorry, I think the blue ones were primary school students. So you've got similar in height, and hence you've kind of got it more closer together, whereas the school students are probably likely to be more spread apart. So I think the two concepts that I want to kind of highlight here is that you have a kind of a central tendency, how closely people are grouped together, and then you also have this concept of a spread, like how far apart your observations are. And this I've kind of brought here to show the difference between a sample and a population. So imagine this is like the entire population of all the university going, I said men, so men and all primary school boys. And then here I've just randomly collected 500 observations. So you might see that this is quite closely shaped to this, but it's not identical, especially with the blue one. It looks really funny in the end. But we want to make conclusions about these two groups. And we might have some particular study that you're interested in these two groups. But we have access to this data. So we want to make measurements about these and then derive conclusions here. So I think hopefully you're starting to see that it's not that clear-cut, because what exactly you get here depends on which people you collected, and it can vary depending on how many people you collected and who exactly collected. Wait, does anyone have any questions? Okay. So one of the concepts I just talked about was kind of the central tendency. So if you saw the children in maybe primary school are kind of grouped together at this height here, which is slightly lower, maybe this, I think I put 130 centimeters here. And people at universities' heights are grouped around here, so 180 centimeters roughly. To capture how close things are in terms of centrality, we use this concept called mean. So in the sample, we often call that average. So this is probably a concept you've come across a lot. It's used a lot in newspapers and so on. But the average is basically measuring how central the data is for samples. So in the example in the previous slide, it's for these groups. So the central value here, which would be somewhere around here, and for here, would be, I think, around here. And that's the mean. So the mean of the sample is called an average. But the mean of the population, the group you're actually interested in, is called the expectation. And what we're trying to do is make conclusions about the expectation based on the average. And next week I'll cover, talk in more detail about when does the average give us a good estimate or like predicts the mean quite well. But just very quickly, I want to talk about notation. You'll often see this notation in papers. So mu represents it's the Greek letter, and this is often used to denote the population mean. So the central tendency of the population, and you could do it for different variables. So in this case, I've done height. So maybe sometimes the researchers would write height here, so that you know that it is the mean of the height. Often they'll abbreviate maybe just to h or something like that. The other concept is actually I'll talk about that in a bit. So the other concept is average. You'll see this more often in data, and you basically take the variable and draw a bar over it, and that means average. So if you have age, again let's go height actually. So if you have height, so as I said earlier, this means this variable is the height variable in general for any given person, and this would be the average height of everyone in your sample. And often they'll kind of simplify it. Maybe they'll represent it by x, and they'll write it like that. I think a key thing to notice here is that it's not too important, but here I've written n, and I've not written n there. And n I've written here to kind of represent how big your sample is. Now the reason I've done that is to kind of the concept I'm trying to highlight here is that the expectation of your population is a fixed number. That's kind of like the true variable we are after. That's always true. Whereas the parameter we are after. Whereas the average, it depends on which sample you collect. So if I was interested in the heights of people at LSE, if I collect, let's say, a sample of 10 people, like randomly pick 10 people, I might get a particular number. But let's say tomorrow I go and collect collect a sample from another 10 people, I might get a different number because it depends on the people I've collected. So that's why the average kind of varies depending on your sample. But this is constant because like LSE I think has 10,000 people, and assuming no one's leaving or coming, which is a crazy assumption, but their heights probably won't change tomorrow. Yeah, so does anyone have any questions? Yes.
What is the difference between mean and average, or is it exactly the same?
So they often use as synonyms, but so the mean is the average. So the mean is the concept of central tendency. So if I just go back to this graph here, so the mean is kind of, this is, I would say, where the center of this is the center here, and similarly there and there. So these are all the mean. But what an average is, the average is the mean of the sample. So yeah, we call the mean of the sample the average, and we call the mean of the population the expectation. Does that answer your question? Any other questions? Okay. Actually, another point I want to make on the mean very quickly is that more often than not, I think I've said this once, but I just want to repeat it, which is that most hypotheses we have are about the mean in some way or the other. And so that's why we're really interested in estimating the population mean, or the expectation. If your question is about do smaller class sizes improve the grades of students, more often than not, the way you state the hypothesis is what is the average effect of having smaller class sizes on the, the mean effect of having smaller classes on the students. So this is why this is one of the most important measures that we use. The other measure that we use commonly and kind of comes into other concepts that we'll touch upon in week 2 and 3, things such as hypothesis testing and so on, is the concept of variability. And actually it'll become quite clear next lecture when we talk about the normal distribution. Don't worry, we won't get into the details of the maths of it, but why we just need these two concepts of variability and mean to kind of describe everything we need. So the standard deviation measures the spread of the data. So when we had these two groups here, we kind of differentiated them in two ways. One was the where the central value is, so where all the data is dumped, and the second thing was how it's spread out. So what variability tries to capture is the spread of the data. Now I think the intuitive, so the way we measure it is something called the standard deviation. Now just to give you so often in papers you'll see the standard deviation quoted. So when you see a regression output, if you've not seen one, don't worry about it, we'll go through that later. But often you'll see kind of a number, and below that in brackets you'll see another number. And the number in the brackets is the standard deviation. Now what the standard deviation captures is the average distance of the points from the average. So that might be a bit of a mouthful, but so what this means is that if you look at this population here, just the blue one, so you've got the average somewhere here. So you've got the average somewhere here. Now, what we want to measure is the distance of every other point from this line. Similarly, we can repeat that same exercise for, we can repeat the same exercise for this group here. And measure the average distance of every point from this line. And what you'll notice here is the average distance is a lot less here than the average distance here. And that's how we capture the concept of spread in statistics. It's not too important, like the mechanics of how it's going about. The main idea is that it is measuring spread in some way. But more often than not, we don't actually quote the standard deviation. What we quote is the variance. Now, this is again just a bit of mathematical mechanics if you're interested. Its variance is basically the standard deviation squared. It's kind of just like measuring something, right? Like you could measure something in inches or centimeters. It doesn't really matter which one you use. It's just that some measures are more convenient than others. Like the metric system, I find it more intuitive to work with, for example. Similarly, variance is capturing the concept of the spread as well. It's just mathematically it has a lot nicer properties, and hence normally we deal with variances and non-standard deviations. I just wanted to highlight this just so that if you come across variance instead of standard deviation, that's why we work with that. In terms of notation, the population parameter is represented by sigma. So sigma would be the standard deviation of the population, and sigma squared would be the variance of the population. And so this is the parameter. And for the sample, we normally represented the standard deviation of the sample within S, and S squared for the sample's variance. So does anyone have any questions about these two concepts of measures?
Can you just repeat that last point? Sorry.
Of the notation?
Yeah.
Okay, so so the way we measure the population, the way we, in terms of notation, how we write down the population variance is by the Greek letter sigma. So often we kind of write var and then the variable we're interested in, so maybe age, I, to represent the variable, and then we kind of write sigma. So the variance is, so this would be the standard deviation, but variance is standard deviation squared, so we write sigma squared in terms of notation. In papers, actually, you might see someone might write age here, just to kind of indicate that this is the age. And for the sample, we often write S as the standard deviation for the sample. And the sample variance hence is just S squared because it's just the square of the standard deviation. Any other questions? Okay, so I think those are the main concepts for today. And I think what I want to do next week is, now that we have an idea of what a sample is, what a population is, and the different measures for samples and populations, so parameter versus a statistic, what we'll discuss next is that how do we ensure that our sample is representative of a population, and when it is representative, when do our statistics give us a good indication of the population parameter, because that's what we really are. Yeah, so that's going to be next week. Okay. Yeah.
Guys, I hope you all enjoyed this introduction to what we're going to be running for the next 8 weeks. I look forward to seeing you all next week's sessions as well. I've been noting down the questions that you've asked as well, so we'll get Manav to write out some explanations of the points that you've raised, and they'll be put on the Facebook group. We've also been recording this as well, so if there's any points you want to go over again, you're welcome to ask and post on the Facebook group. Or email us, but there'll always be the recording that you can go back to as well. And just one last thing, I have to plug that we're recruiting at the moment for the blog and the journal editorial board. So I don't know how many of you are second and first year students. There are some first and second year students in here. Okay, fantastic. Well, the positions are all open to all undergraduate students, whatever your subject that you're interested in. If you want to come and talk to me about it at the pub, we're going to the pub now. You're welcome to do so. You can also email me. All the details are online for these positions. So yeah, do get in touch. And I will just, on a final note, anything that you sort of haven't picked up today, or you think that you need some more help on, we're really seeing this as a collaboration between us as students as well, and we really want to help make this the best opportunity for you to sort of grasp these ideas. So do give us feedback. Ben's going to put up an anonymous feedback form as well. So if you don't want to come and talk to us in person, that's fine. We don't mind. You can post it online, and we'll really appreciate your feedback on that, and we'll feed it back into future weeks' courses as well. Okay, really hope you've enjoyed it, guys. And there's some biscuits when you walk out as well. Okay.